Well, good morning. And I'm delighted to be in this great place with Schrodinger and Boltzmann. I'm teaching undergraduate quantum this semester, and I've told them I'll come back with lots of stories about them. So if you know stories you can share, please do that. I really want to thank the organizers for putting together this wonderful workshop and for inviting me to that. I'm going to talk about quantum spin liquids, and I will focus on this very special property of spin liquids that the excitations are not like those of a regular magnet, and what are the challenges in detecting them. So let me start by introducing my students and postdocs and my collaborators on this work. So Xie Feng, he's a graduate student who has now gone as a postdoc to TU Munich. Adip Agrawal from IIT Kanpur, Shubhra Bhattacharya from ICTS, and a lot of that work has been published. Also, so we have been using exact diagonalization, DMRG techniques like this. We also like to counter that with various kinds of variational wave functions and mean field theory to get insight. More recently, we wanted to look at techniques that are not influenced by the finite size limitation. And so we collaborated with a group of Tao Xiang and Kang Wang. And toward the end, I will talk about some unpublished work on the dynamics of these excitations, which turns out to be really the most promising way to look for these signatures. And that work is with Xu Yang, who has now moved back to China, and Ryan Bukele, my graduate student. Okay, so let's begin. So broadly, spin liquids, it's a new phase of matter. So there's clearly a lot of interest in going after them, but there are many challenges. The most significant is the materials challenge. And to date, we don't have really good materials to go after. And here we need really some theoretical input that designs the main principles behind them. And that's where a number of people in this conference have played a significant role. Then after the design, the actual material has to be made, and there are aspects of disorder and so on coming in. Another significant route that has emerged is using synthetic, like Rydberg atoms, to create such spin liquid dominating interactions. So that's a very significant growth. That's here. And what I will be focusing on today is a little bit about standard probes and why they are not sufficient, and going towards some new probes. I won't really get into this, though this is where a lot of my effort is also now going. Okay, so let's step back and look at this absolutely fascinating phenomena that happens when many electrons interact, and under special conditions, you can get fractionalization. So for example, the first level of fractionalization happens even in a Mott insulator, where the charge degrees of freedom and spin degrees of freedom separate and exist at two different energies. So the charge is at a very high energy of order the Coulomb interactions, and the spin is on the scale of the exchange interactions. In spin liquids, we see a second level of fractionalization where the spin itself is not a good quantum number and fractionalizes into anyons. And the main challenge is, and we know this theoretically for certain models, so it's very enticing to go look for these, but the main challenge is that finding a sharp signature of these fractionalized excitations so far has not occurred. So what I'm going to do today is, this is the big question I'm asking, but in order to make progress, I'm going to work with a specific model, the Kitaev model, And within that, I will see what are some of our results and how some of these results can be generalized for quantum spin liquids in general. But in order to make progress, I have to work with a particular model. But it does contain some of the essential features of a spin liquid. So, so I'm going to show you two main results. The first is I will show how multi-spin correlations, so going beyond what is measured in inelastic neutron scattering, where you measure two spin correlations at different times, so it's a dynamical response. Here we want to look at multi-spin correlations, and remarkably, these show sharp signatures. I will also look at toric code, which is even yet a further simplification of the Kitaev model, which has only the gauge degrees of freedom. And here I will show you how pump probe nonlinear response can actually see signatures of braiding. Okay. So very quickly, if you're an experimentalist with a possible material, the first signature to look for before any spectroscopy is to look for the spin susceptibility, and by looking at 1 over chi, pull out the theta Curie wise. And you want to look at this ratio, theta over Tc. And typically I've seen a lot of materials where theta over Tc, if it's of order 1, that's a typical ordered magnet. But if you start getting large numbers for this, like 10 or 50 or 100 or even more, like some of these organics, those become good candidates. And they should not be ignored. So the ideal spin liquid would be where Tc is 0, but let's not wait for that ideal material. There may already be things you can pull out when the frustration ratio is large. And the main idea would be to explore the region in temperature between Tc and theta. These would be dominated by the quantum spin fluctuations around, hopefully, an underlying spin liquid state, which is, of course, getting obscured by an ordered state. But this region would already be interesting to explore. Okay, going forward, inelastic neutron scattering has been the way to look for magnetism. And here, typically, if you have something like La2CuO4, it's a Mott insulator, which is an antiferromagnet. It has a long-range order, which results in these goldstone modes that are gapless with a linear dispersion, and all this has been beautifully mapped out. Now let's take another material. So let me put up the whole thing. So this is alpha ruthenium chloride, which is also a Mott insulator, but its spectrum you can see is nothing like what you saw in the ordered antiferromagnet. So this is, of course, a theory calculation of the Kitaev model, but also the experiments show that again, in an intermediate regime, you get this very broad, like a Rothko painting. So no features. Of course, there are these sort of regions of color, which tells you some intensity is varying. So the key point here is local moments exist, and we know that from the susceptibility. We also know they interact strongly, but there are no well-defined modes. Okay, so let me give you our result. Our result is the following. That let's say I compare a Kitaev model result. So I will give you explicitly what the model is, but it's essentially a model on a honeycomb lattice with frustrated interactions. And let's also take a Heisenberg interaction on the same honeycomb model. So if you look at a one spin flip excitation, a correlation of this kind, which would be measured in inelastic neutron scattering. So you start in the ground state, flip a spin at site J, flip it back at some other site I at a later time, and do the Fourier transform. In the Heisenberg model, you get these sharp modes, as I mentioned. In the Kitaev, you get broad signatures. However, what we find is if you do the two spin flip operator, so at a site J and its neighbor, you flip two spins and then flip them back at a later time and Fourier transform S2 of Q and omega, that in a Heisenberg model is broad. And we understand why, because one spin flip creates a magnon, two spin flips creates two magnons which can scatter against each other. And in other words, if you give the system some energy and momentum, it can share it among the two excitations in multiple ways. And that's what leads to a very broad signature. However, if you do the same operator for the Kitaev model, we find that the excitations are sharp and they are also directional. They are not uniformly moving in 2D, but they have some directionality. And this is what we would like to propose as the quantity to search for. Okay, so what in the rest of the talk, I want to show you how this result comes about and what might be ways to look for these two spin flip excitations. Okay, so for those, I'm sure many of you are familiar with this model. It's a celebrated model. It's really a very profound result to have an exact solution in 2D. The model is defined on a honeycomb lattice with qubits at each site, or spin half at each site, and these are really J half. We heard Ginyat's talk. So we need spin orbit coupling. I'm going to, at this point, not include any phonons, which I realize are important, and these could be invoked later as a way to probe the magnetic system. But for now, I'll ignore them. So these are your J half or spin half qubits, and they interact with different Pauli operators on the different bonds. So the X operators interact on the blue, the Y on the green, and the red and the Z on the red. And that is what causes frustration. So this qubit in the center doesn't know how to order given the three very conflicting interactions on the three bonds. And that's the origin of frustration that doesn't allow this honeycomb set of interacting spins to order. And what Kitaev showed is that this system has topological order and long-range entanglement. Now, those are hard to probe theoretically, and that's why we go toward the excitations. Okay, so the way Kitaev solved it was to take that spin and fractionalize it into 4 anyons. 3 of those, which are indicated with color, form the link variables, and then if you go around, it becomes a plaquette variable. So that's a gauge theory, a Z2 gauge theory. And the 4th Majorana, the black one, is I'm going to call the matter Majorana. So that Majorana can then move in the presence of these gauge fluctuations. And the problem of the spin interacting with other spins now is redefined in terms of anyons. So matter anyons interacting with gauge fluctuations. So what we have is an emergent description of matter and gauge fields. So this is characteristic of any strongly interacting system, that you will have emergence of new degrees of freedom, and typically these will be gauge theories, and matter interacting with gauge theory is a universal theme, not just of the Kitaev model, but in general of any strongly interacting system. So on this, we have obtained the whole phase diagram now. So Kitaev solved the problem exactly at this point, and a little bit perturbatively, this axis here is a magnetic field applied perpendicular to the plane of the honeycomb. You can apply it in different directions. And I'm showing this right now for a Kitaev constant, which is antiferromagnetic. So when the field increases, at large field, we would expect a polarized phase, but we find another very interesting intermediate gapless phase. On the other axis, this is another axis that could be tunable. In a material, you would need some kind of strain. In these Rydberg atoms, you can just engineer it. But this axis takes one of the coupling constants, Kz, and makes it stronger than the other two. And the advantage of doing that is when Kz is equal to Kxy, at this point, you have the matter Majoranas, which are forming like a graphene spectrum. But beyond some critical value of kz over kxy, this is 2, you enter a phase here where the matter Majoranas actually get gapped out and the fluxes, which were the gauge degrees of freedom, become the low energy description. So these are things to keep in mind. Where I'm going today, I'm not going to describe much of the phase diagram. I'm going to give you some idea about why these two spin flip excitations could harbor something sharp a little bit on this axis and on this axis. I just want to mention that, just like these, our high energy people, we also have a primordial fractionalized phase, just like they have a primordial universe from which everything emerges. We really believe this is the phase to understand. This has all the degrees of freedom interacting the gauge and the Majorana. And then from this, actually, as instabilities, all the others emerge. Okay, but I'm going to skip this. Okay, so let's come to fractionalization, and let's say you have a neutron coming in, and it makes a local spin excitation, and that excitation fractionalizes into a Majorana plus Z2 fluxes. So here I've shown this is the Majorana, and these are the fluxes. So inelastic neutron scattering mixes these 2 degrees of freedom. But now, let's look at the dimer dynamics. So I'm going to now excite 2 of them. Okay, so let's say I go back, I do a sigma Z operator at this site, and that creates a Majorana and these 2 fluxes on that bond. But if I do again a second sigma Z on this site, that creates a Majorana and 2 fluxes in these adjacent plaquettes. So it's mixing Majoranas and fluxes. But so basically 1 spin flip is mixing, but if I do 2 spin flips, then it creates 2 Majoranas and 2 fluxes in each plaquette. But since it's a Z2 gauge theory, 2 fluxes is equivalent to no flux. So that's how 2 spin flip has gotten rid of the flux degrees of freedom, and now you have only the Majorana response left, which can be observed cleanly without the interaction with the fluxes. Okay, so that's kind of what is behind this idea. Okay, now I further want to describe how these, you might still ask, isn't the signature still broad? It's still being shared between 2 Majoranas. So isn't the signature still broad? And I want to show you how, because of a directionality with how these excitations move, it becomes a sharp excitation. So here I go to the toric code, and you take the large Kz limit, as I mentioned, and in that limit, one of the bonds is becoming stronger. So what that does is you can go into another basis where you define another qubit on the bond. So that would be in this with antiferro interactions, it becomes this Hilbert space of up-down or down-up. So that's my tau qubit. And now in terms of tau, you can do 4th order perturbation theory and get an effective Hamiltonian in terms of sort of these star operators, which is basically sitting at a site. So here is the effective lattice, the effective square lattice that emerges. And on this square lattice, so you'll get many interacting squares, you can have the tau x operator on a site, which is usually called the star operator. And you have a non-commuting tau z operator, which gives you like a plaquette flux when you go around. So in terms of these 2, you can write an effective Hamiltonian, and that's called the toric code Hamiltonian. And what is interesting, this has excitations which can be bosonic. So you can have excitations of the star operator where you maybe you flip a spin, or you can have it of the plaquette operator where one of the links is changed. And those are bosonic excitations, like magnons. But on the other hand, if a M or a plaquette object, if a vortex, M you can also think of as a vortex, goes around the charge, it picks up extra minus sign and becomes a fermion. So underlying these anyons in the Kitaev model, they have different statistics. And the question I want to ask is, can we see the statistics of this in any kind of spectroscopy? Okay. So yeah, one more thing. So now again, you can see the power of doing two spin flips. If you do one spin flip, you go from this low energy sector to a high energy sector. That's what happens when you flip a spin. You go into the higher energy sector. But if you flip two spins, you return to the low energy sector. So that's another reason to be using two spin flips. Okay, so now these excitations, E and M, are static. When you just take the toric code and you create these excitations, they will just sit there. But if you add a field, just like we did before, it gives a dispersion to these anyons. And you can see, importantly, this involved the tau x, this involved tau z, and this has the third operator, tau y. So it commutes with one, it doesn't commute with either, and that's what leads to the dynamics. Okay, so if you now look at S2 of k and omega, so what am I doing? Taking the ground state, applying a dimer operator, which is two spin flips on a bond, and then returning to the ground state. And you can put the dynamics in that. That is S2 of k and omega. And what that shows, this is as a function of omega. So you see multiple peaks. This axis here is H, this is omega. And you see there are multiple peaks. So that is the signature of fractionalization. Each peak means something very particular. So let's say I focus on the lowest peak and map out, if I sit at that energy and I look in momentum space, you see there's a very clearly dispersing mode. And this mode is a collective mode of these anyons. Okay, so I'll show you a picture of what that looks like. But first, it's important to notice that if one was doing S2 of Q and omega, sitting at that particular energy and looking in momentum space, there would indeed be these very sharp dispersive signatures in momentum space. And a way to understand why this signature is not broad, because it is creating multiple anyons, why is it not broad, is that these anyons that get created, let's say a star excitation and a plaquette vortex, as the field is applied, they have a dynamics which forces them to move together. This is this, animation from, you see they are forced to move together because of the gauge constraints. And that is what leads to this signature remaining sharp. Okay, so a quick summary at this point. Essentially, two spin flip response is very powerful way to probe fractionalized excitations, and in different ways you can remove the signatures of, let's say, the vortices and only observe Majoranas, or if you do, this was with the sigma z operator, this is with sigma x on the bond, you get E and M excitations that move together. And the very last part, let me address the the statistics. And here I go to, so the experiment before would be something you could probe with an NV center. And we are having some discussions how with Jacobi's group, how noise spectroscopy could probe that kind of a four-spin correlator. Now I turn to a pump probe nonlinear response. And here there's some beautiful work, including by Yong Beck, and also very important earlier work by Van and Armitage. And what this technique does is the following. So instead of measuring some response function in the ground state, you first pump the system into some excited state. So first you apply a pump and excite it into some state, and then you probe the system, and then you basically do your measurement in that pump state, and then it returns back to the ground state. So there's a pump pulse at t equal to 0, a probe pulse at time tau 1, and then a measurement. And this allows you to probe higher order spin correlators of this kind. So like involving 4 spin correlators. And you can control their direction by the magnetic pulse direction, magnetic field of the pulse or the probe. So here you can change it from Z to X to whatever. And we will utilize that. Okay, so you want to take the signal and remove the linear response pieces, and that is what becomes the nonlinear signal, and that is a higher order susceptibility. So let me just quickly give you the main idea here. So at t equal to 0, let's say you apply an mx. So mx commutes with, say, the star operator. So in the plaquette part, it will create, it does not commute with, say, the plaquettes, so then it creates 2 of these vortices. So here are the 2 vortices that are created. At time t1, you apply mz, and that creates 2 e particles. And these can then braid around each other for some time, and then you measure them back, and then they annihilate when you go back to your ground state. But it is this braiding that you can capture in the chi3 when you measure it as a function of these times. And you have to allow sufficient time for the anions that are created to braid around each other. So what is our signature? The signature, actually, I wanted to mention this important reference by Parameshwaran. Based on their paper, we have been influenced a lot by some of their ideas. Okay, so here is the main result that we find. So if you look at XXXX, which basically means all the operators here are in the X direction, that only creates the E particles. And E's braiding around other E's are like bosons, so you get, let's say, a particular sign. And this essentially what we would call is no braiding of, so the bosonic statistics doesn't give us any answer, or I should say it gives a background. Okay, and this response essentially decays, and it's proportional to the linear response. So it's very good. We have a check on the response functions. But if you excite X, Z, Z, X, so this is X, Z, and then Z and X, then that creates E and M particles that braid around each other. And that, because of the braiding and the interference, you get an enhanced signal. You get some growth in the dynamics. And so the chi3 has the following form. Multiplying a sinusoidal is this function here. The XX part just decays as 1 over t, but this part which has the braiding has a part that grows as square root of t. And that is what we are looking for, a divergent behavior coming from braiding. So using ED and DMRG, we can disentangle that. And we have indeed seen that when it was the XZZX, there is this time dependence of that square root t, which shows this very strong growth, whereas the other one is decaying in time. So our main message is that, in this pump probe, people have been Fourier transforming the 2 times, the tau 1 and the tau 2, the 2 times can be Fourier transformed. And you look at this 2D coherent spectroscopy maps. And our point is, do not Fourier transform. Look directly in the time domain to see this delicate divergence signature over a background to deduce the braiding statistics. Okay, so with that, let me reiterate and come to my conclusions. The outlook for spin liquids, we really do need more quantum materials. And they don't have to be the perfect ones with Tc equal to 0, but even ones where the separation between theta and Tc is large. We also need more synthetic platforms for making such spin liquids. And you might ask, how are, here we had this very beautiful, because of spin orbit coupling, there were 2 pathways that was shown by Jacqueli and Kalulilin, where these electrons could go from exchange pathways between, say, ruthenium using the ligands. There were two pathways, and that's what gave rise to the Kitaev. How would that be replicated in a synthetic platform? It's a totally different idea there. Using Floquet, they can literally make different gates interact. So you can have the XX and the YY and the ZZ, but none of it is using spin orbit coupling. So using Floquet engineering, they are creating these synthetic platforms, which is quite powerful way, alternative way. And then I would really encourage observation of these two spin flips along different experiments like noise spectroscopy and also pump probe ideas. And more than just the spectroscopy, the fact that we can also distinguish the statistics is really powerful. I don't think there are many experiments that can do that. So these are some of our publications here. And this is something I haven't talked about, but I'll be happy to discuss. We also looked at, okay, I've talked about the Kitaev model, which is a strong coupling result of some underlying Hubbard model, where you might have had electrons hopping on a lattice, and then you take a strong coupling limit. And in general, you would create, by symmetry, many interactions, J, K, gamma, and so on. And they must usually arise just by symmetry. But if you can ask the following question, what kind of a hopping model would give rise to such a Kitaev model? It turns out the hopping model is a flat band model. So just one flashing there. So if what we find is the underlying Hubbard model requires that the hopping between different orbitals be dominating over hopping between the same orbitals. So this is the J3 half manifold, that's the J half manifold, and you see how different the widths are. This width is extremely tiny because it goes like not just the hopping. Usually the widths are on the order of hopping. Here it goes like hopping square divided by the spin orbit coupling scale. So you can get extremely flat bands. So what this says is that the material platform may be even broader, even if they are not Mott insulators, but strong spin orbit coupling is strong. The metallic states could also lead to very interesting flat band states, like we have seen in these Kagome metals. So there's a connection between the flat bands, which can arise from frustration in one language, also leading to spin liquid candidates at strong coupling, where frustration has a very different meaning. But both are frustration of some kind. Here it's frustration of hopping, not the nearest, the same orbitals are not connecting, but for some reason the different orbitals are connecting, but that physics is intimately related to the design of the Kitaev interactions at strong coupling. Okay, thank you very much.